welcome. We're going to be going over colligative properties, specifically freezing point depression, boiling point elevation, osmotic pressure, and vapor pressure lowering. So there's 4 equations associated with each of these colligative properties. But before we go into that, first of all, it helps to know what colligative properties are. Colligative properties are properties that are determined only by the number of particles that are present in solution, not by the identity of those particles. So, in cases of ionic compounds, we have to take into account the fact that ionic compounds separate into ions. Colligative properties, and generally these are referred to properties of a liquid solvent. Properties usually of a solvent that depend solely on the concentration of dissolved particles. Not the identity of those particles. Now I can tell you this, that colligative properties are always dependent upon the solvent. Colligative properties are always dependent upon the solvent. That's the other factor. Okay, so let's list them off. The 4 colligative properties. First of all, we'll do vapor pressure lowering, which basically is that the vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. That's vapor pressure lowering. Also, I believe this is sometimes referred to as Raoult's law. Okay. Secondly, you have boiling point elevation. Delta TB is equal to KBM, where the M in this case is the molality, the KB is the boiling point depression constant, and the delta TB is the change in the boiling point. Now this is where I'm going to actually start to deviate from what the book is telling you, because mathematically speaking, what the book says regarding the delta change in freezing point is actually wrong, or at least less accurate. Books sometimes indicate change in freezing point with 2 different equations. Sometimes they have a negative KFM, sometimes they have a positive KFM. But it's more proper to speak of the change in freezing point as negative KFM mathematically, because when you add salt to a solution, the freezing point goes down, not up. So the change should be negative. And then the last one is the osmotic pressure, which is sometimes actually just listed as a pi symbol, osmotic pressure is equal to the molarity times RT. Molarity times RT. This is in fact the same exact formula as the ideal gas law. Because molarity is volume over number of moles, right? Or actually, no, molarity is moles over volume, sorry. Moles over liters, moles over volume. So if you look at this, if we look at osmotic pressure equals MRT, it's really PV is equal to nRT. It's the same as the ideal gas law. It's kind of interesting. Okay, so let's take a look at applications of these. But first I want to discuss real quickly general principles. If you add solute to a solution, are you more likely, or do you think that the solution will have a higher vapor pressure or lower vapor pressure? What is it?
Higher.
Actually, it actually tends to have a lower vapor pressure, because the vapor pressure is directly proportional, or at least some way proportional, to the amount of solvent molecules that are on the surface, right? But if you have a lot of solute, dissolved in the solution, then some of those solute molecules are on the surface. And not only are those solute molecules on the surface, but those solute molecules are attracted to the water particles or whatever the solvent is, so they're actually not only blocking them, they're also pulling them down. And so in both of those cases, they prevent the solvent from escaping as easily. So the higher the concentration of solute, the lower the vapor pressure. And it has to do with mole fraction. So if you have 50% solvent, it's only going to have 50% of the vapor pressure. If you have 25% solvent, it's only going to have 25% of the vapor pressure. So, likewise with delta T, change in boiling point, since boiling point is by definition the temperature at which the vapor pressure is equal to the atmospheric pressure, since you're lowering the vapor pressure, you're also going to be making it harder for it to boil, right? Because the vapor pressure can't get up to atmospheric pressure if it's lowered, right? So you end up having to add more heat and keep pumping heat into it until it reaches a higher boiling point. So the more solute you have, the higher the boiling point. Interestingly enough, for freezing, it's the opposite. Freezing lowers the freezing point. So it extends it in both directions. It raises the boiling point and it lowers the freezing point. The reason that solutes lower the freezing point is because the solute particles block. They get in the way of, like, for example, water or some other solvent crystallizing. The molecules can't link together because the solute particles are in the way. And so it can't form a regular crystal structure, and that prevents it from solidifying. And so you really have to take away a lot more energy to get it to crystallize around those impurities. And lastly, osmotic pressure. We know from biology that things always flow from areas of high concentration to low concentration, right? So effectively, when you have a semi-permeable membrane, and on one side you have a lot of solute particles, and then the other side you have relatively few. Nature likes equilibrium. It's trying to reestablish equilibrium. Well, if the semi-permeable membrane prevents the solute particles from going back and forth, what has to happen is that the water pushes through. The water pushes through from one side to the other to equalize the concentrations. Since this has a higher concentration of water, in other words, it's less concentrated with solute, the water is going to be pushed from this side over to this side. In order to dilute the left side and make it the same concentration as the right side. And that pressure, that pushing from water from the less concentrated side to the more concentrated side is called osmotic pressure. So now that we know what each one of these is, time for some crazy calculations. Because unfortunately, these are not necessarily always very easy problems to do. So let's take a look at number 1. So what is the boiling point of an aqueous solution of 6 molar HNO3? Gives the Kb for water is 0.51 degrees Celsius per mole, and the density of the acid is 1.125 grams per milliliter. So, which equation should we be using here?
The second one.
Yeah, the second one. And what do we have of the second one? What information do we have about the second one? Given in the problem.
KB.
We do have Kb. So, and this problem, our Kb is actually 0.51 degrees Celsius per mole. What else do we have? Molarity. Is this equation called for molarity? That's molality. Not the same thing, right? Unfortunately, we have to convert the molarity to molality. That is not an easy job. That is a very complex calculation. So, the first thing we're going to do is break apart molarity into its component pieces. Molarity, 6 molar. Would you agree that if I say we have 6 molar HNO3, that effectively means that we have 6.00 moles of HNO3 per 1 liter? You all agree with that? Yeah, so 6 molar, we break it up into its conversion direct form, 6 moles per 1 liter. To make this problem possible, I have to assume a particular volume to work with. I'm going to go ahead and assume 1 liter, because that will give me 6 moles, and I'll make it easier. Because remember, what is molality? What is molality? Molality is the moles of solute over what? Kilograms of solvent. And what's molarity? Moles of solute over liters of what? Solution. Solution. Solvent and solution are not the same thing. I can't simply convert this to kilograms. I actually have to separate out the solute. So, I already know if I assume 1 liter, I already know the moles of solute, right? It's going to be 6. That's pretty easy. But the kilograms of solvent is the pain. So the first thing I need to do is convert the liters of solution to grams, or milliliters, because it gives me the density, right? The density is 1.125 grams per milliliter. Since I have liters, I'm first going to have to convert to milliliters. 1,000 milliliters, 1 liter. Next, milliliters can go on bottom, and I can convert to grams, right? 1.125 grams is equal to 1 milliliter. I could convert to kilograms at this point, but I'm not going to. Okay, yeah, I do. So I'm going to go ahead and convert grams to kilograms. And this will give me 1,000 grams is equal to 1 kilogram, right? And that's going to leave me with 1.125 kg. So this is one piece of the puzzle. One piece of the puzzle. So that's what I started with. Okay. This is the kilograms of solution. Now I have to remember that solution is equal to solute plus solvent. Solution is equal to solute plus solvent. I got the solution, I need to get the solvent, so what else do I need to solve for? If I want to solve for the solvent, what other piece do I need?
Solution.
What?
The solution. That's all.
Well, I have the
Okay.
solution. I have 1.125 kilograms of solution. And I need to find the kilograms of solvent. Looking at this equation, what's the missing piece? What do I need to solve for the solvent?
Solution.
The solute. I need to know the kilograms of solute. Now what's my solute? HNO3, right?
Yes.
HNO3 is my solute. So I have to find the kilograms of HNO3. So I'm going to go ahead, switch colors here, and I have to start with the amount of solute I know I have, which is 6.00 moles. And then I'm going to go ahead and convert the moles of HNO3 to grams of HNO3. You remember how we do that? What do you need to convert moles to grams?
We use the molar mass.
The molar mass. So, HNO3, I need the molar mass. All that stuff in Gen Chem that you thought you wouldn't have to use again, it's coming back. So 14.01 for nitrogen, 1.01 for hydrogen. I have 3 oxygens, 3 times 16. Gives me 48. 14.01 and 1.01. That adds up to 63.02. So I am going to use 63.02 grams per mole. Now I need to get to I'm going to go to kilograms because I need kilograms of solvent. So grams, kilograms. My writing is not as neat as I would like it to be. And then what does that give you? 6 times 63.02 divided by 1,000. You got your calculators? Let's pull them up. Or use your phone if you have to. So 0.37818, but you only need can have 3 significant figures. So that's your kilograms of solute. So now I can plug this into my equation. 1.125 kilograms of solution is equal to 0.378 kilograms of solute plus the solvent. Subtract 0.378 from both sides, and sorry, I get my solvent mass, which is what? What is it?
0.747.
0.747? Okay, so 0.747 kilograms of solvent. Good. I can now finally go back here and calculate my molality. 6.00 moles of HNO3 over 0.747 kilograms of solvent. And that's going to give me my molality, which is what?
.03.
8.03? Looks good to me. So now we have our molality 8.03, except we maybe don't. This is the molality of HNO3, right? HNO3 is what kind of an acid? Strong or weak? Strong acid. And what do we know about strong acids?
They will split.
They completely separate into ions, right? So that means, how many ions is HNO3 going to break up into?
2.
2. So even though this is our molality of HNO3, our molality of particles is actually going to be what? (16.06). Okay? Because remember, colligative properties only depend on the concentration of particles. It doesn't matter what those particles are. If this separates into ions, then those are separate particles. So this is going to be not 8.03, but 16.06. 16.06. Now I can calculate my delta TV. I'm going to erase this over here, so I have more room. This is then going to be equal, delta TV is going to be equal to 0.51 degrees Celsius per molal times 16.06 molality of particles, which is equal to what?
(8.1906).
8.19 degrees Celsius. Now that's just the change in temperature. So remember that the change in the boiling temperature is actually equal to the temperature, the boiling point of the solution, minus the boiling point of the solvent. And what's the boiling point of an ordinary solution of, or rather, what's the boiling point of water normally? Because it says this is aqueous solution.
100.
100, yeah. So basically, is 8.19 degrees Celsius is equal to the temperature, boiling point of the solution, minus 100 degrees. So then all I have to do to get the boiling point of the solution is add 100 to both sides. And the boiling point of the solution is at long last 108.19 degrees Celsius. I'll add an extra 0 here so I can keep all the sig figs. 108.19. Pretty easy, right? Just kidding. So, that's the problem with these colligative properties problems. They can often involve multiple steps, and it can be easy to get lost in the process. So, always come back to focusing on the central equation. What are the things that you have? What are the things that you're missing? Figure out those things that you're missing. Go back into the equation, solve for those things, and then get what you need to solve for the final problem.
Hey, one more time. How can you get 1606 from A03?
It's because, and I'm going to go ahead and erase this up here. A little definition. It's because when you're talking about the molality, or even mole fraction, molality, or any of those other equations, molarity, it's always the molarity of particles. It's not the molarity of the compound. And when HNO3 dissolves in water, it breaks apart into H plus and NO3 minus ions. So if there's, like, for example, if there's 8.03 moles of HNO3, for every 1 mole of HNO3, you're going to get 2 moles of particles. 2 moles of ions. Does that make sense?
Yes.
So that's why that times 2 gives you 16.06. And since this is moles per kilogram, this ends up being moles per kilogram.
Okay, thank you.
Yeah, no problem. All right, let's take a look at the second one. Now, the second one is interesting because this is actually one that you're going to actually have to do for lab upcoming. I don't know, have you done the colligative properties lab, the freezing point depression lab? If you haven't done it yet, you're probably going to do it either next week or the week after. So the next question is going to be exactly the type of calculation you're going to have to do for that lab. I'm going to erase all this. Is that okay? Okay. I want to make sure I'm not rushing you along. All right. So for this next one, it said a solution containing 1.25 grams of an unknown solute dissolved in 25 milliliters of cyclohexane freezes at negative 11.4 degrees Celsius. What is the molar mass of the solute? And it gives you the Kf for cyclohexane and the normal freezing point and the density. So, what colligative property are we talking about here? Freezing point depression. And what's that freezing point depression equation? Yeah, delta Tf is equal to negative Kfm. Very good. So, for this freezing point depression problem, you'll notice it actually is not asking for the freezing point, right? What's it asking for?
Molar mass.
Molar mass. It's asking for molar mass. So what's the equation for molar mass? Or what is molar mass? What's the grams divided by the moles, right? Molar mass is the grams for 1 mole. So we can actually use that as an equation. Since we're looking for the molar mass of the unknowns, we need to know what the grams of the unknown are, and we need to know what the moles of the unknown are. Does that make sense?
Yes.
So the grams of the unknown are actually given, right? What's the grams of the unknown? 1.25, yep. But we're not given the moles of the unknown. We're given a bunch of information relating to this. So what we might want to do at this point is see what kind of information we have, and then see what we can solve for with it. Okay, so what information do we have?
The freezing point, right?
We have the freezing point of the solution. It says it's negative 11.4. We also have what? TF of solution, negative 11.4. What else we got?
We have KF.
We have KF. KF, in this case, is 1.86 degrees Celsius per mole, right? No, it's not. It's 20.4 degrees Celsius per mole. What am I thinking? All right, so what else do we have?
We have the density of the
So yeah, we got density of cyclohexane, which is 0.7885 grams per milliliter. What else do we have?
Normal freezing point.
What'd you say?
Normal freezing point.
The normal freezing point, the freezing point of the solvent. And that's 6.6 degrees Celsius. And do we have anything else? We have the volume of cyclohexane, don't we?
Yeah.
25.00 milliliters. All right. So, if we're going to use this equation, what's the delta TF?
Going to be
Negative 11.4.
No, it's not going to be negative 11.4. Remember, this is change in freezing point, right? How would I calculate change in freezing point?
6.6 minus negative 11.4.
Actually, no. When you're doing change in freezing point is actually always the temperature of the solution minus the temperature of the solvent, the pure solvent. So that means this is going to actually be what? What's the freezing point of the solution?
11.4.
Negative 11.4. So it's negative 11.4 degrees Celsius minus 6.6. So you had them flipped. And this is important because the answer you get is a negative. It's a negative what? Negative 18.0, right? If I did that math correctly in my head, which I think I did. So that's your delta TF. What else do you have? You have the KF, right? So that means if we have delta TF and KF, we can solve for what? The molality. So looking at this equation up here, if I want to solve for molality, I can just divide both sides by negative KF. I'll rewrite that equation. That's going to give me molality is equal to net delta TF divided by negative KF. You all see where I got that equation from this? Okay. So now I'm just going to go ahead and plug in the values that I have, which is I have a negative here and a negative 18.0 degrees Celsius up on top, and on the bottom I have 20.4 degrees Celsius per mole. So the two negatives here are going to end up actually canceling out, and I'm going to end up with what?
1.88.
Not 1.88. Did you multiply by 2?
I think so.
You did, didn't you?
0.88.
0.88. How about 3 sig figs?
0.882.
0.882? molality. Yeah, remember, you only multiply by 2 if it breaks apart, but it actually says this is an unknown molecular solute. We're going to assume this molecular, which means it's not going to break apart, because it probably wouldn't dissolve in cyclohexane if it was ionic. All right, so now what we're going to go ahead and do, we have molality, and remember what molality is? What's molality? What's molality? Yeah, moles of solute over kilograms of solvent, right? And to solve for the molar mass, what do we need? Solve for the molar mass, what do we need? The moles of solute, right? We need the moles of solute. Do we have the moles of the molality? Yeah. Do we have the kilograms of solvent? No, but we could. We could, right? Because we have the density of the solvent and we have the volume. We can get the mass of the solvent, can't we?
Yeah.
So, what I'll do here is I'll take my volume of cyclohexane, 25.00 milliliters. I'll convert it to grams using the density. 1 milliliter is equal to 0.7885 grams. And then I'll convert my grams to kilograms. I could stop here. I could stop here and then plug it all into this equation. Yes?
I don't think it makes a difference, but on paper it's 0.7785 density.
Oh. 7785. Oh, yeah. Sorry. No, thank you for pointing that out. One of the most important skills in chemistry is attention to detail. So, good on you, man. Thank you. So now, we have kilograms. There's 2 ways we can actually do this. We can actually take this answer and we can plug it in here along with the molality and solve for the moles of solute. Or we can just use molality as a conversion factor. Because remember, molality means moles per kilogram, right? So I can actually just write this in as 0.882 moles per 1 kilogram. Moles per kilogram. And then I'll solve for moles directly that way. So 25 times 0.7785 divided by 1,000 times 0.882, what does that give me?
I got 0.01716.
0.017 what?
16.
0.01716. Now, strictly speaking, we only have 3 significant figures because this only had 3 significant figures. But you don't want to round to the very end anyway, so we'll keep it all for now. So now that I have the 0.01716 moles, I'll pop that into this equation, 0.01716 moles, and I'll divide my grams by my moles, and I'll get my molality. And what is my molality? Where's your calculator, young lady?
$72.842.
Yeah, 72.8 grams per mole. And that is the molar mass of the compound. Now, why would you ever want to use this? Well, the truth is, it's very valuable for analytical analysis of, say, for example, if you don't know what a compound is, like this unknown compound here, if you're doing, like for example in organic chemistry, we can devise what the formula of a compound is based on certain spectroscopic techniques, which tell us what type of atoms are present. But if we don't know the molar mass, we're kind of like lost. We don't know if we're not sure exactly how big or small the molecule is. The molar mass helps us to narrow it down and determine what the formula of a compound might be. So, are any of you planning on taking organic chemistry? Nobody? Okay, well, I'm not. Okay, maybe one? Okay. Well, basically, you'll see how useful it is to have the molar mass of an unknown compound in a short time. I won't go into it in too much detail since most of you are not.
Oh, wait. So, I'm kind of confused on
Sure.
the formula, like the one you wrote in blue. So, isn't that formula used to find molarity, or is it molality?
Molality.
Okay.
Yeah, this is molality here.
All right. So we found that, right? Like
Yep.
point. So why do we have to use the moles of the solute over the kilogram of the solvent?
Well, what I'm saying is, I was reminding you what exactly molality meant. So, the molality is the moles of solute per kilograms of solvent. See, here's the thing. You can either plug the molality in here as a conversion factor, or you can substitute in the values here into this equation. 0.882 molal is equal to the moles over the kilograms of solvent, which basically in this case are whatever that number happened to be, if you equaled it right here. And then you can plug that in there and solve for the moles, basically. But for me personally, I think using conversion factors is just a little bit easier, a little bit faster.
And so you converted milliliters to grams.
Using the density, yep.
Okay.
Anytime you have a fractional unit like this, you can use it as a conversion factor, and that's very useful. All right, cool. Let's take a look at vapor pressure, shall we? So good old Raoult's law. Says, what is the vapor pressure of an aqueous solution of 2.5 molal NaCl? It sounds so weird, doesn't it? Molal? Who came up with that? All right. So, once again, since it's vapor pressure, in this case we're using Raoult's law, which is the vapor pressure of the solution, is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Now, here's the thing. Mole fraction of the solvent is equal to the moles of solvent over the moles of solvent plus the moles of solute. In other words, the total moles. In this problem, we're not given the moles of solute though, right? Nor are we given the moles of solvent. We're given molality. 2.50 molal NaCl. And since we know molality is moles per kilogram, I could break this up into its conversion factor form and write it as 2.50 moles of NaCl per 1 kilogram of solvent, which in this case is water, right?
Yeah.
Because it says aqueous solution, so this is actually 1 kilogram of H2O. Okay. So if I want to find the pressure of the solution, I need to first find the mole fraction, right? Because it kind of gives me the pressure of the pure solvent, doesn't it? What's the pressure of the pure solvent in this case? What's the pressure of the pure solvent?
23.77.
23.77. So this is 23.77 millimeters of mercury. So I just need to find the mole fraction of the solvent. Well, fortunately, I have the moles of something. What is this the moles of? Somebody said it, I think. The solute, right? This is the moles of the solute. But I don't know what the moles of the solvent are, right? So I got to calculate that. How would I calculate the moles of the solute? Or solvent, rather. What do I start with?
You're gonna find the kilogram of solvent first.
Yeah, I start with a kilogram of water. And if I want to convert it to moles, chances are I'm going to have to convert it to grams first, right?
Yes.
So kilograms to grams. So 1,000 grams is equal to 1 kilogram. So now that I have grams of water, what's going to come down here? What unit goes on the bottom? Grams, right? Whatever was previously on top, there's grams of water. What's going to go on top? What am I going to convert grams to?
It's moles.
Moles. I need to know the moles of water, right? I need to know the moles of solid. Now, how do I convert grams to moles again?
Divided by the molar mass.
Molar mass. And the molar mass of water, that's 16 plus 2 is basically 18. 18.02 if you want to be precise. And then I just multiply across the top, divide by the bottom, and what do I get? 1,000 divided by 18.02?
55.49.
55.49.
55.49.
Okay, 55.49. That's the moles of water. So now I have all the moles I need to solve for the mole fraction. I'll go ahead and plug that into here. The moles of the solvent, 55.49. Over the moles of the solvent, 55.49. Plus the moles of the solute. Now, how many moles of solute do I have? 5. Good catch. Not 2.5. 5 moles. Why? Why is it 5?
2 particles.
2 ions. It's an ionic compound, right? NaCl will break apart into Na plus and Cl minus. And when we do the colligative properties, we have to keep in mind it's the moles of solute particles that we care about. Moles of solute particles. So this is actually going to be 5 particles. 5. I am so proud of you. You remembered that. That I think is the first time I've ever run this workshop that anybody's actually remembered to multiply by 2. Good job. All right, so 55.49 divided by 55.49 plus 5, so divided by 60.49. And what does that give you for your mole fraction?
.917.
I'm sorry?
0.917.
0.917. Very good. I apologize for my deafness. 0.917. I actually need one more sig fig.
3.
3. Okay. Good deal. Because yeah, this is 4, and when you add these up, that's still going to be 4, so this will be 4 sig figs here. So now I have my mole fraction, and I have my pressure of my solvent. I can go ahead and solve for this. This is equal to mole fraction 0.9173 times a pressure, 23.77. And that gives us our answer, which is
21.805.
21.81 millimeters of mercury. 21.81 millimeters of mercury. Oh, that's 21, sorry. Whoops. Behold its splendor. Okay. Now, number 4 is another vapor pressure problem. And because we're running a little bit out of time, I want to make sure we get to the last colligative property, which is osmotic pressure. So, any questions on this though before we go to osmotic pressure? Make sense?
A little bit about it, and I'll ask.
Alright, yeah, no problem. Alright, I'm going to go ahead and erase this. This at least wasn't as bad as some of the others, right? Alright, so now, cruise ships do not carry water with them. The reason they don't carry water with them is they have to carry an awful lot of water for cooking, cleaning, showers, and things like that. It would just not be practical to take on so much fresh water. What they do instead is they have a system called a reverse osmosis system on the ship that takes the seawater, the salty water, and extracts pure fresh water and uses it for everything from showers to cleaning to anything else. So, so an average shower contains 17.2 gallons of clean water. How much seawater would be needed for the reverse osmosis system to produce enough water for a shower if the reverse osmosis system has a running pressure of 55 atm? That's 55 times atmospheric pressure. That's a lot. And a running temperature of 25 degrees Celsius. It says, note that seawater has approximately 1.25 molar in dissolved particles. 1.25 molar in dissolved particles. Okay. So for something like this, we have to use, of course, the osmotic pressure equation, right? So, as I showed you before, you have the semi-permeable membrane, right? And then you have all these seawater particles, all these salts and contaminants and other things like that on the one side. And you're trying to squeeze it out. You're trying to squeeze pure water out of it. The only problem is there's nothing on this side, okay? And if there is water that gets on this side, it's going to want to push back this way, right? So you need to push the other way in order to overcome the osmotic pressure and create a net pressure in the other direction to push water through this membrane. So you need this massive external force. And the massive external force is this 55 atm running pressure. 55 atm. So the question is, what concentration can you bring this to before the backwards pressure is so much that it won't let you go anymore? Because this will only be able to concentrate this until the osmotic pressure. So this is the external pressure, this is the running pressure, the applied pressure. And the running pressure has to overcome the osmotic pressure. Right? Running pressure has to overcome the osmotic pressure. So basically what has to happen here, I have to figure out what sort of concentration will this allow me to get before the osmotic pressure is equal. So I plug in the osmotic pressure as 55 ATM, because at 55 ATM, I no longer am producing any clean water, right? The pressure this way is equal to the pressure this way, and no more water can be squeezed out. Does that make sense? So then, that's equal to the molarity times RT, and R in this case is the ideal gas law, because what molarity is moles per liter, right? And the running pressure is ATM, so I'm going to use the 0.08206 liter ATM per Kelvin mole. Okay? And then for temperature, it says it's at 25 degrees Celsius. Of course, I have to use Kelvin, and that's 298. I have 273, right? Y'all remember how to get Kelvin? Okay. You want me to go over that, or is you good?
Okay.
Good? Okay. So now, all I have to do is divide both sides by R and T, and I get my molarity. If I do so, I see that my molarity is going to be 2.25. That's the maximum molarity I can concentrate this to before the reverse pressure is so much I can't squeeze any more water out. All right. So I know that my initial molarity, my final molarity, my initial molarity of the incoming seawater is 1.25. And the final molarity is going to be 2.25. So how much water do I need to have to squeeze out 17.2 gallons of clean water? Well, for this, I'm going to go back to my old pal from Gen Chem 1, the dilution equation. M1V1 equals M2V2. Alright? So this side can be my unconcentrated initial, and this can be my concentrated final amount of liquid. In this case, this is the dilute solution before it gets concentrated into the concentrated solution. Now, the molarity initially is 1.25, right? And the molarity finally is 2.25. Now here's the thing. If I want to squeeze out 17.2 gallons, that means that my final volume, volume 2, is going to have 17.2 less gallons, right? I'll have squeezed out 17.2 gallons, won't I? So it'll be whatever the initial volume was minus 17.2 gallons. So I can then substitute those values in. So for V2, that'll be V1 minus 17.2, and this will be just V1. I can now do a little algebra and solve for V1. So 1.25 V1 divided by 2.25 is equal to V1 minus 17.2 gallons. I then subtract V1 from both sides. That leaves me with 1.00 over negative 1.00 over 2.25. V1 is equal to negative 17.2 gallons. And then if I multiply both sides by the reciprocal here, negatives will cancel out, and I will get a volume initially of 38 point something. Sorry, I kind of rushed it a little bit with this particular problem, but I know that I was supposed to end at 12:30, so I didn't have a whole lot of time. So it's 38.4. I don't know. 38.7. 38.7 gallons. Does that make sense? Cool. So that's how these colligative properties problems work. They can be a little tricky, they can be a little bit complicated and multi-step, but if you break it down piece by piece, you'll be able to handle it. All right? Any questions over that? Yes?
So, okay, how did you get the 2.25 for the final molarity?
The 2.25 came from this section up here. I simply took my
Oh, you divided.
yeah, my molarity is equal to 55.0 divided by 0.08206. 98.
And how come we couldn't have just plugged in the given molarity into that formula, or the even the final reference formula?
Well, if you put the given molarity, that would just give, if you put like the 1.25, that would just give you the osmotic pressure of the seawater. But you're looking for how much seawater is needed to produce fresh water. And the fresh water is produced by the pressure of the osmosis, reverse osmosis system. What'd you say?
That says a lot.
It is a lot. It is a lot. Hopefully, though, this will make you a little bit more prepared when you go into class.